What is up, AP Stats? This is our crash course review. What I've decided to do is take a lot of the StatMedic stuff, and I have all the slides here. And basically, what I'm going to do is in about an hour and a half, give you maybe even less. We'll see. But basically, give you the idea of all of the different components that you could face while on the AP exam. So we're going to kind of get going here, and we'll rock and roll. All right, so buckle up, and here we go. We got Ryan with us, and some of you are slackers right now, but you will be coming in later on, I'm sure. So just touch base, and let's go from there. All right, the first thing we want to talk about is the different types of graphs. We know that we have a histogram. Just as a heads up, just some thoughts here. The difference between a histogram and a bar graph is something that has space in between. It also is more categorical. Most of statistics is quantitative. So anytime that you look towards any of these dot plots or box plot or stem plot, these would be more quantitative measurement. By the way, stop me as I go, okay? And we'll rock and roll. So as we go through, we notice that, like for instance in this histogram, we've got something that's more skewed to the right, pulling the tail towards the right-hand side. And we know that. We also know that, like, we could read this is any value between 1 and 2 for whatever context we are. We have on the left side the frequency amount. The only thing that I would say to this that's incorrect on all of these is please be sure, especially on an FRQ, to make sure you label this, okay? Make sure you label these on the bottom. What does that represent? What's the context of what we're talking about? That is very important. Also on a stem plot, I know I'm kind of going all over, but when we look at this, remember that like if I was looking at 1 and a 2, this would be 12, right? So just make sure that you remember that. And as we go from there, just a heads up on that piece. Also, in order to make a key, we would want to say that 1/2 is equal to 12, maybe students or whatever the context would be. And just make sure you label the key in order to get that full credit that's there. Also, a dot plot is always on the AP exam, so it's something to remind yourself of. Remember, anytime I'm comparing a quantitative measurement, we go into what we call SOX, shape outliers center spread, and make sure that we also add context to it as well. Some other things that I've seen counted off on the AP exam is if, let's say, on the dot plot, I was supposed to compare this. So if I was to compare it, one thing to remember is if I'm comparing, I can't just say, this is A, this is B, this is C. I actually have to go into, like with my shape, I would compare one to the other, okay? So just a kind of a reminder there, just some things that a lot of times people get counted off for, that is there on that side, okay?
For the dot plot question, which distribution has the smallest standard deviation?
Yeah.
I just don't really know, like what determines a small standard deviation?
Yeah, well, first off, a standard deviation, we're kind of going all over, and again, these are just little tidbits, not necessarily the StatMedic, but just things that kind of go off of these slides. Standard deviation is the average distance from the mean. Okay? So if that's the definition, then we know that the average, the mean would be somewhere about right in here, right?
Yeah.
Well, what would have the average, the smallest average distance from the mean? That would be down below. Okay?
Yeah.
So remember, when we talk about shape, we know what to say. Skewed, normal, approximately normal, bimodal would be shape. Outliers, outliers would be your outlier formula, right? So that would be like 1.5 times IQR plus Q3 and 1.5 IQR minus Q1, right? And anything that falls outside of that range would end up what we call be an outlier in that way. So for instance, this right here would be related to this formula because it's plus Q3 and it's outside of that value. So that would be an outlier. So we put a little dot there as far as a box plot goes. One thing also to remember is that this is still the maximum. So when I do the range, it would still be my max minus my min to find what my range is for that, even though there's an outlier on that outside.
So if that's an outlier, why do you put the last tick mark right there?
Because this is the next highest amount.
So you still have to do that. Okay.
Yep. So that's still the next highest, other than the outlier that's there. Okay. Thought I was gonna say one more thing in terms of standard deviation. Okay, here's something too. We probably will hit this in a second. If so, we'll just skip right on by. What would be a good measure of center for this specific one here?
A good measure of center median.
Median, because median is resistant to outliers. Resistant to outliers. Mean is not, right? So median would be a good one for the center if I was doing socks. What would be a good one for shape? I'm sorry, spread. Sorry,
IQ.
spread. I could use IQR is a good one, or range, right? Either one of those two would work because those two are both resistant to outliers. Standard deviation would be more towards something that's approximately normal, such as the dot plots. That would be good. And the mean would be a good one if it's approximately normal as well on that side. So just as a heads up reminder of that, okay? Cool. Again, these are all quantitative measurements when we're looking at this here. All right, one other thing too is that both of these are skewed to the right. You say, Coach, why is this left side? Well, you have to kind of look at it as if it was flipped on top of this, because you have to look from the lower to the higher. So just be careful. That is something that some people will mess up on that part there. Okay. I think I actually got ahead of myself with the socks part. One thing to remember to use on any of these is make sure you use ly words for especially shape. So if something is exactly normal, say that it's normal. But if it's approximately normal or fairly normal, we want to make sure we soften it with ly words. So approximately normal or fairly normal. What's that?
How would it be exactly?
Exactly would be like if it was perfectly normal. Everything fell on the mean, and then it was equal on both sides.
Or do we do slightly skewed?
Slightly skewed, that would be perfect. So anything that kind of softens the blow a little bit with that. All of this stuff on the top side is something that, again, the outlier formula or unusual features, that all of this stuff is good. Just make sure you remember to include that context on any time that I'm there, okay? The one thing, too, is that socks, make sure you do not use DOFs, okay? Or don't use socks on least squared regression lines, right? Because what happens? Well, the least squared regression line goes with DOFs. We'll talk about that in a little bit, okay? All right, so if I were to give you, let's say, the number of hours of sleep, I gave you a sample size of 10, and I said out of these 10, describe the distribution, the first thing I would have to do is first draw, right? And then once I drew, then I would go into socks plus context, right? So just be sure to know how to do that.
Why would we know to draw it?
Because there's no way to describe the distribution unless you do draw it, right? I don't care how you draw it, just make sure that you do it somehow, some way. Dot plot's always a really good one. It's always probably the easier of the options, but that's up to you there, okay? Another thing, too, is make sure you know how to put values into L1, especially on this, just as a heads up. I'll kind of show you this just so that you've seen it. Go from there. Do you remember how to do that, Ryan?
Yeah.
Okay.
Just the bars.
Yep, you'll go to Stat Edit. So Stat Edit. Make sure, let's say these were the values just for time's sake. You could then go into, so again, Stat is there, but you go Stat Calc. It's actually Stat Calc, 1 bar stats. And then your calculate would be there, and then it gives you all your stuff. Your mean, your sample standard deviation, your population standard deviation, sample size, so on and so forth. Okay. All right. Good stuff. Again, hopefully you're getting some of this down too as you're going through there. The next part is your DOFs. Your DOF stuff is now chapter 2 or section 2. This moves more towards your least squared regression line. This is, I use DOFs because I usually say outliers, but this could also be unusual features. So outliers or
This is my
unusual.
struggle area.
This one right here? Okay. So if we were to describe the heat bill and we see something along the lines of what we see here, remember that the line is the line of best fit,
Yes.
right? So this line is called my least squared regression line.
That's why.
And what does it do? It minimizes the residual. You don't need to know how to find it. You just need to remember that it minimizes the residual, okay? Traditionally, they'll give this to you. The key is, what do I do with it? So y hat, let's talk about that. That would be my predicted, okay? The predicted. So what does that mean? That means that this dot is the actual, is the A, and the line point is my predicted, okay? Just a reminder of that. So to get the predicted of the least squared regression line, we could substitute something in for x, 50, 60, or whatever. And we could get out what the y hat is, or the predicted value of y. Traditionally, they would prefer you, instead of putting y and x in, to put that in context. So we would say heat bill hat equals 273.58 minus 3.6 average temp is my x, okay? That would be in context of what we were trying to see here. How would you describe this in context?
There is a strong linear negative relationship.
Strong, linear, and I wouldn't even say it's fairly linear. It's linear. Negative
Relationship with, do I have to say with no outliers?
with no unusual features or outliers.
Between heat bill and average temperature.
As it relates to average temperature to heat bill. One thing too with least squared regression line that everyone needs to remember is that least squared regression line is not used to use cause and effect, right? We can only say that there is an association. So I can't say, wow, sorry, I slipped, I don't even know. Association here, we can't say that an average temperature as it declines, that the heat bill will decline. But we can say that there is an association, right? The only time I can say cause and effect is if there's a random assignment, right?
Okay.
And that's if I go into more of an experimental design.
Okay.
This is just observational. Interpreting slope, this is just something to remember. If I interpret slopes, like up here, I would say that as, literally you're just interpreting that. So negative 3.6 over 1. So as this is the rise over run, right? Yeah. So this is rise, so as y over x. So as the y decreases by 3.6, the x will increase by 1.
So
now,
as the heat bill decreases by $3.60, the average temperature will increase by 1.
Yeah, and I would say the average temperature would yeah, as far as the slope goes.
Or like, don't we have to say predicted?
Exactly, that's why I was trying to fit that in. So as the heat bill decreases by 3.6 degrees, we would expect the average temperature to increase by...
We would predict that.
Hold up, I said the heat bill, so I said in degrees. As the heat bill decreases by 3.6...
$3.60.
Yeah, $3.60, we would expect the average temperature to have increased by 1 degree Fahrenheit.
So
yeah,
expect or predict is the same thing?
Exactly.
Okay. Mm-hmm. And then interpreting R-squared.
R-squared is the, whatever this is, right? By the way, this is really tight. To find R, we just simply take the square root, right?
Yeah.
Okay, so that's R would be correlation. Closer it is to 1 or -1, the closer that it would
Wait.
be.
I
In
thought
this
we usually
instance.
use R squared to see the correlation.
Well, you could use that as well. It's
So
just a little different.
R is the correlation?
R is usually just correlation. R squared is called the correlation coefficient.
No, that's what I meant.
And this means that 98.9% of the variation in y can be accounted for by the least squared regression line. It's basically going in a little bit more depth of like, as this varies from one actual to another, it can be accounted for as it changes in the y. So as y changes,
Okay.
it could be accounted for by the least squared regression line.
Okay.
Just be familiar with that and make sure that you have an idea of that interpretation if you've seen that. Again, that is correlation coefficient. Cool. This goes into a little bit more detail. As we look at this is the least squared regression line, but over here this is called our residual. Now, a couple things in order for LSRL to be a good representation of this model. There's a couple things with the residual. First of all, it needs to be scattered. And second, it needs to have no pattern. If that is the case, and you could check off both, then we could say that an LSRL is a good model to represent the actual data itself, okay? So as you can see, there's nothing crazy there. So we could say that it is random, has no pattern or curvature, therefore it is a good representation. Think of this as if we just took this line right here, and let's say we took this line right here, and we just pushed this up, pushed this down, and just kind of went straight across. That's literally what this is. And as we do it, it's just an easier way of seeing our residuals. So we call this a residual plot, right? Residual plot. And remember, what is residual? It's the error. So it's the error from one of these, which is my actual, to my predicted, which is the actual line itself, or the point on the line, okay? All right, it says find the predicted bill for a month with an average temperature of 42 degrees. Well, 42 degrees is what is represented with X. That's where I just simply plug it in. So 273.58 minus 3.6 times 42. Make sure you write the formula first, okay? Write it in context, plug it in, give me an answer. Okay?
Okay, 122.38.
Okay? Yeah, 122.38. The next thing is the actual bill for a month with average, is this 122.38, right?
Yeah.
Make sure you show work. I'm not right now because I'm going quick. The actual bill for a month for average temperature was 120. Calculate and interpret the residual. Well, this was the predicted, right? It's predicted.
The actual bill was
This is the actual,
Oh, okay.
right? So what is the actual minus the predicted? Well, that would be my residual. This would be 122.38. This can also be,
Wait,
I'm sorry, 120,
Yeah.
my fault. So
Under-
120 minus 122.38, which would be negative 2.38. And again, it can be negative. It just means that that's, the actual would be below the line. So
Okay.
that would be completely okay, right?
Yeah.
And is a linear model appropriate for the data set? Don't use R here, okay? So we're not using R. R is the strength. But when we talk about whether it's a linear model or not, we go straight into the residual plot up above.
So
Okay.
we would just say a linear model is appropriate because the dots are scattered and there's no pattern in the residual plot.
Bingo. If the data appears nonlinear,
Yeah, I don't know.
use a nonlinear model to calculate a predicted bill for a month. I would just say for this, if you ever see something where they give this to you here, okay, right here, just know where the log is on your calculator and know how to plug it in. That's all I would say to that.
Where did they get those numbers?
I don't even think, I would say for this one, let's skip that. We'll take the loss on that if they bring that up because I've not seen that on chapter 2. All right, sampling methods. All right, so we have a couple of things. Remember, I don't think we actually have a problem with these, so I'm not going to go too much into them. The vocab is the key, so like convenient sample is if I'm just going to give an example. So this would be like outside the lunchroom. Basically, it's trying to do things the easy way without randomly sampling there, having anything that basically allows us to have a representation of the population. So outside the lunchroom, those that come in first or whatever. Voluntary response would be, that's exactly what it says, is if people volunteer. Simple random sample, this is the good method. This is where we do our whole population. And we take a sample at random from them. Yes, ma'am?
What's the difference between a convenience sample and undercoverage? Because if it's a convenience sample, isn't there going to be undercoverage?
Correct. Yes.
So undercoverage is not a type of sample. It's just the way that it's biased.
Yeah, undercoverage contributes to bias, but it's basically what will happen when you have bias.
Okay, so there's the things that contribute to bias is undercoverage.
And it does not representative of population, and it's excluding a certain group.
Okay.
So think of it like if we were trying to figure out what people thought about the new uniform policy that GAC is going to next year.
Wait,
If
what?
people were trying to think about that, then what they would do is then go outside of the lunchroom and do that. But what if the shirt and ties that are coming next year were not going to be what people liked? But let's say the first people to come in were like more studious or something like that, and therefore because it was a convenient sample, everyone said, "Hey, we like it," and therefore it's not representative of the population, and would produce undercoverage.
Are they really trading the uniform?
For Thursday, chapel days.
Wait, what?
Yes.
There's more top speed. Yeah.
How to do on SRS?
Wait, so what's non-response?
Oh, non-response. So yeah, this is non-response is if no one responds, or if a lack of people respond. So like, you ever get those email surveys and you're like, yeah, I don't really want to do this.
Yeah.
That would be a non-response.
But that's not undercoverage? Well, I
Non-response
guess
is
they
also in this.
received it, but they just didn't respond.
I would say non-response is also in this category of different forms of bad sampling.
Okay.
But the actual bias in and of itself would produce, oh, I see it down right here. These are the sampling issues. Does that make sense? So if I have a convenient sample, then, oh, how about this? If I have a voluntary response sample, that is a bad sampling method. That produces a bias of non-response and could also produce a bias of undercoverage.
Okay.
Does that make sense?
Yeah.
Response bias is also something where people lie. So as we look at that, just a heads up there. How do we do a good SRS? We did this the other day, but we would make sure that we label. We would, so pick a number through a random method. I don't care how, just make sure it's a random method. Sorry, rep method. Ignore repeats if needed, right? Sometimes we don't, depending on the method. And ignore numbers outside of my range. Now, if you did a piece of paper and had everyone's name on it, and I selected 10 people, well, I wouldn't have to ignore numbers outside of my range because it's not relevant, right? You guys have a great day. We'll see you. Does that make sense? We're good there? Okay. Stratified versus cluster is also something too, as we look at that, that's a little different. I want to make sure I hit on this because sometimes people struggle. A cluster would be I take the population, okay? And what I do is I divide them up into different mini clouds. Okay? All right, I don't know what type of mini clouds those would be, but one thing to remember is that one of these mini clouds is like, basically, it should look like the big cloud. Got me? So like, what I mean by that is, if I go and I randomly select a class at GAC to be able to talk about the uniform policy, right? That would not be a good representation of what my population is. But if I have homeroom groups or small groups that have freshmen, sophomores, juniors, and seniors in them at random, and then I randomly select a certain number of clusters to sample everyone inside, that would be appropriate, okay? A stratified is different because in this, think of this as the population. I divide it up into certain groups, okay? So maybe I do use freshmen, sophomores, juniors, and seniors. But then I randomly select a certain number within each group. So maybe I select 10 in this group, 10 in this group, 10, 10, 10 to produce a total of 50, right? So this would be like a total of 50 that is randomly selected, but it's a little easier than trying to do an SRS in that way, right? Plus, it actually would be a better representation if I do have separate groups that are there, okay?
So, like, why would we, like, you know, when they're like, which method is better? Why would a cluster ever be better? Like, I never see, like, a reason to have, like, a cluster.
Yeah, so sometimes they want you to list the positives of both, the negatives of both. A lot of times a cluster sample will be more convenient. So if you were trying to think of all the stores across the entire world for, trying to think, all the stores for, I don't know, just pick a random store. So all the McDonald's in the world, and I was to randomly select, trying to get a customer like, are they happy? Are they not happy? It would be a lot easier to actually go to 10 different stores or 100 different stores and sample all customers that come in, rather than doing 10 random customers from every store in the nation or in the world. So that would be
is from the 10 stores.
Correct. I sample everyone in that store, so to speak. Whereas stratified, if I was doing stratified,
anywhere.
it would be every single store I would select 10
Okay.
from each of those spots. Does that make sense?
Yeah.
And the difference between cluster and a block, like.
Oh, yeah.
Okay, so this is different. This is observational, right?
Okay.
So this is
Blocks are
more
experimental.
observational. When we go into the experimental world, a block is an experimental stratified sample.
So,
If that makes sense.
I don't
And
know
I'll
if
show
this
that.
might be stupid, but, like, what makes it observational? Like, I think that, like, because you have the data, then that's experimental because you have the data.
Not necessarily. Observational is you're chilling. You're going and saying, I want to know customer appreciation. So you go to McDonald's and you simply say, are you satisfied? You give them a survey. That's observational. Got me? What we did with Turner, observational. Once you end up having your hand on the actual way that you're conducting the experiment, that would be experimental. So think of that as like, we end up taking a pre-survey, and then we go into McDonald's, and we improve the customer experience on how they get their food. Maybe it's not through face-to-face, but they go to kiosks and then go. Once I do that, then I then say for those specific stores, we do a post. Because I now have my hand on the data, let's say I randomly assign those that did, those that didn't, and then compare, that would be an experimental design. So we could then show cause and effect because of the fact that we have random assignment now. Okay? So this would be more observational. And we cannot show causation. All we can do is simply say what? There's a correlation, right? Or there's a tendency for something to be higher or not, or whatnot. We're just simply observing, right? And really, to be honest, we can't even say correlation, because like even with Turner, we were trying to figure out whether their ratings were going up or down, right? We can't say that this definitively, like, we can't say that this causes this, though.
So when we do, okay, I know we're going to future chapters, but like when we're doing four-step process and stuff like that,
Mhm.
you know how sometimes on multiple choice questions they ask like sometimes the answer choice will be like, well, this is an observational study, so like you can't conclude this. Like, does that make sense or no?
I think you can conclude it, you just can't say
Yeah.
what's causing it.
Correct. That's it. So we could conclude that
The
Yeah, the
are going
ratings were
down.
pretty
When I
We
think
can't say
conclude,
why.
I think
Correct.
cause. That's why I think it trips me up because I think when I think concluding, you're just that you're concluding that it caused.
remember Turner. So I always want you to go back to that. When you came in there and you provide conclusions to your analysis,
Yeah.
you provided maybe these are some ways. There's no way that you could have shown cause and effect in that.
Okay.
You know what I'm saying? Now, if you were to, and this was maybe a way that you could have improved the study, if you said, well, why are the ratings declining?
Yeah.
Well, let's do this. Let's go ahead and implement one. Maybe we'll try to just see, does customer or does viewership increase if you did more of like a fantasy basketball thing while the game was going on?
Yeah.
Why don't we try that out for about a week's time with a certain random people and find out whether that created heightened enjoyment from that. That would be cause and effect. When you say your conclusion, you're simply saying this, did it decline or did it not decline, right? Or did we reject or fail to reject, right? That would be, does that make sense? You can't say what caused it though.
Yeah. Okay.
Cool. Not definitively, at least. All right.
Oh, confounding variable.
One thing, too, I forgot about this, is that when I do this from the stratified, make sure that these 10 that are selected are mini SRS.
Yeah.
So it's like I'm doing a simple random sample.
SRS.
Yes. This is not as convenient, but this is probably a better representation more than likely. This is a lot more convenient, and if done right, it's still good representation on that.
So when we say, okay, we split it up into groups, and like they're like explain how you can use this method, how you could use Stratify.
Yeah.
You'd go, we take this group, break it up into smaller groups with context, and then do you say and select an SRS of 10 or select like 5 SRSs, like of each group?
I would
like,
I would just say within each strata,
oh, okay.
within each group, same thing.
Okay.
I would take a simple random sample of 10 individuals within each of the groups of whatever context I'm
Okay.
talking about. Good question. All right, there's something else I highlighted.
What's the
Select
difference between stratify random sample and simple random sample again?
Say that again.
The difference between stratified random sample and simple random sample.
Simple random sample is if I took 10 people at random, 50 people at random across the whole GAC high school. I would put everyone's name in a hat, select 50. It's possible to have 30 freshmen, 10 juniors, 1 senior, and 9 sophomores, right? It's possible. But if I want a better representation from all groups, what we do is we divide them up into certain strata. So the strata would be our grade levels. So that means that I would have freshmen, sophomores, juniors, and seniors, and then I would take a stratified random sample or simple random sample from each strata or from each group. So 10 freshmen, randomly select, right? Put their name in a hat for freshmen, sophomores, juniors, and seniors. Why we do that is it would mean that we would have a better representation of the entire population because we'd have 10 from each.
Okay.
Right? Usually you would pick the variable that would most impact the results in your mind, right? So the new uniform policy coming to GAC, if I were to do that for all of y'all right now, and we had, yeah, exactly, you wouldn't care. In fact, you probably would want it to be harder just for the fun of it, right? So that would definitely skew the results if we were to do it without a stratified. Does that make sense?
Is that an example? They actually have a new dress code change.
I was joking. I was actually, I put that on the podcast, but Che and Jackson
Yeah,
were in
no,
here.
I didn't know if you were were joking.
and I was totally
like,
messing, and I don't know if they were listening or not,
Yeah, no,
but it was good.
Che was listening.
Yeah, no, I think he was worried a little bit. All right, this is 3.2, so we're just kind of going. We're
He
just
was like, yeah, on Thursdays during chapel. I was like, wait,
Yeah.
what?
I said, yeah, Thursdays during chapel, we've got ties next year. You know? All right, so as we go through this, couple things on this. We have what's called an explanatory and a response. So if I was to look at the Turner thing, I'm going to keep coming back to that because I think it's good in the context of this. So if I look at what is the response, we talked more about the response, did we not?
Uh-huh.
The response was the fact that they had low ratings, right? Or lower ratings. But the explanatory is what explains. I want to see what explains the response. Is it because of the fact that it's the announcers? Is it the lack of fan experience? Is it the lack of social media presence? What is it? So we're going to pick something, right? Whatever the explanatory is. Now, if we looked at, let's say, the average AP exam of Stats Medic versus the review book, right? The type of review would be the explanatory. The response would be the actual score itself.
Okay.
Does that make sense? But that would be the explanatory versus the response. A confounding variable is something that does what?
Skews the data.
Yeah, it has an impact on the data.
Is it
So-
confounding?
It's like lurking, right?
Is it lurking? Yeah.
Yeah, it's kind of like that. Lurking, confounding variable. So it
Okay.
has an impact on the results that a lot of times we can't control. In every study, there's going to be lurking variables that are going to impact our results every time.
It doesn't look like lurking. I don't know what that is.
I'm sorry. L-U-R. I'm not lurking.
Okay.
All right. So if we draw an outline of an experiment, okay,
Am I right?
and then we'll go into what it would be in terms of the block design.
Yeah.
But I would have 100 students. By the way, make sure you explain this. Don't just draw the outline. Draw the outline, but you have to go into a lot of depth,
Can
right?
we go over an FRQ of one of these? Or
This
delay?
would be good. Can we do that at the very
Yeah,
end?
yeah, okay,
Is
yeah,
that cool? So yeah, just trying to do it like
yeah. Oh, okay.
if there's 100 students and I randomly assign, so we randomly assign, okay, into two groups, group 1 and group 2, we have 50 each, okay?
Yeah.
In group 1, let's say that, actually we'll say that this is with Turner again, okay? We have 100 different people, okay? And we could even make them voluntary. You say, why? Well, it's not an observational experimental. So then once I randomly assign them into 50-50, that's okay. So once I get into group 1, maybe in group 1 we just give them the, this is the control group. So this is the group that just watches the experience just normally.
Okay.
On the group 2, this would be the group that would be more or less like, maybe it has a heightened fan experience,
Okay.
whatever that would mean, okay?
The game in person.
Yeah, that would be helpful, right? And then afterwards, we would then compare the results.
Yeah.
So we compare results. And I would even add something in there. In the control group, maybe we give them a survey of some kind, or maybe we give, I mean, that would be the only way I think that you could maybe look into that. But that would be perfect.
So you're
Right.
a young coach?
I don't know what that was.
Don't lie. Yeah.
Yeah, it's cute, right? All right, so what we do is we could just compare and show that random assignment, that which would be better, right?
Yeah.
Which would be better. Now the next thing is what is the difference between an experimental observational? We've already kind of talked about that, right? We can show cause and effect with experimental. Observational is we're just chilling,
Correlating.
and we could just say that there's almost a correlation that's there.
You just find a relationship between it.
Yeah, it's the relationship. It's the conclusion, right? It's a relationship between what we're looking at, okay? The big thing, too, with an experiment is we have a treatment. A lot of times has a control group, or we're comparing two different methods, which could be possible as well, okay? Yeah, the advantage. What's up, Charles?
Yeah, coach, there
You
you
see,
go.
man. Advantage would be obviously what we just talked about, can show cause and effect. Now, a block design is something where if I have 100 people and I was to say, well, there is a difference between males and females. A block is not something that's random. Just like a stratified, it puts people into specific groups. So maybe we go ahead and say, you know what, we're going to go ahead and put males versus females. And then what we're going to do is we're going to say that that's a block. That is not random. Then afterwards, we're going to go into random assignment. Random.
Look at you doing it again.
You know what? Tell on me. That's fine. Let's say there were 60 males, 40 females that volunteered. That's fine. We'll put them in there. When we randomly assign into group 1 and group 2, we'd have 20 and 20. Okay? All right. Once we do, we then go into control versus the fan experience, and then we simply compare.
Okay.
Y'all follow me on this?
Yeah.
Same here and here. Group 1 would be 30. Again, you would want to talk through this. Group 2 would be 30.
So we don't compare
C,
the block?
and then compare. Say again?
Do we compare the?
No, because they're going to be separate.
Yeah.
That's why we divided them up.
Alright.
But then afterwards, you could basically say, with male and females,
Just,
you could have 2 different kind of mini experiments that are going on.
Okay.
Does that make sense? All right, remember stratified's observational. Experimental is, a block goes with experimental.
Okay.
Okay? If you think of like this is the stratified version of an experiment, then that would be appropriate. An observation would be stratified.
I forgot
Okay.
about this setup thing.
Yeah, just so if they say design an experiment that yada 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 yada, then you could go from there and rock and roll off that. By the way, just a little shout out. If you have not seen Charles's old school Minecraft video, you are missing out on life.
Machine.
You are missing out on life. And his little. All right.
That was entertaining.
All right, this right here is the number 1 most difficult part on the entire test. It's the least favorite out of all AP statistics, okay?
Oh, I hate this.
I don't need
What
you
is
to I don't need you to memorize this. I just
Yeah.
need you to be familiar, okay? So let's talk about what mutually exclusive is, okay? Mutually exclusive means, and I'm going to really dumb this down, it means that 2 things can't happen at the same time.
I understand.
Can
the
happen.
definition.
Yeah, but I
At
understand the definition, but like if those
same
get recognized, that's
time.
that's where it gets
Okay?
wrong.
Independent, what does that mean?
That one can't happen without
One thing
Doesn't
does
affect
not
the other.
affect the.
affect the other, okay? If something is dependent, think about the jelly beans, or I think we did the
M&Ms.
beads or M&Ms, where if I selected one red M&M, I said, what's the probability of selecting another one? That is a dependent event, right?
Yeah,
However,
but you don't
because
know.
it passes the 10%, it doesn't matter. Does not matter. We can proceed with our 4-step process, okay?
So okay, let's take the M&Ms. How would M&Ms be dependent on each other if you don't know, like, if there's not like a select number of each color?
Technically, is there a finite number of M&Ms?
Yes.
Yes. Okay? Now, and even over the course of the entire world, there's a finite number. But if I said, what is the probability of me selecting 2 reds, and I select one, eat it, select the other, eat it, that probability is dependent, right?
Yeah.
But the probability is so small, we don't care. So this is kind of moving away from probability and more into our 4-step process, is that because of that, if something is dependent, we just simply can go ahead and use the 10% condition. And what that does is that's like the trump card
Yeah.
that basically says it doesn't matter whether it's dependent or independent, we can proceed.
So if they gave me an FRQ saying like, is this like independent, and we said it wasn't independent based off like the context itself, do we say like, can we continue it by proving the 10%?
If they then ask, can you continue this by using an 4-step process, I would say yes. And then they say explain, because of the fact that 1/10 of the sample size is still greater or still less than. I gotta write it out. It's still
1/10 is greater than
yes is
the-
greater
the
than
sample size.
correct. If we do that, if we could say that, then we would say we're still okay.
Okay, but it is mutually exclusive because you can. Well, no, it's not.
I want to separate them. Does that make sense? I don't want it to. I want these two things to be like a line that divides down the middle. Because if you try to mix those up, yeah, you're gonna mess up. Okay, you're gonna really mess
But
up.
it is possible to have both those at the same time, though, correct?
Wait, something? Yeah. How do you do?
Yeah, like a deck of cards.
Yes. So something
We
that
can
Be
have-
mutually exclusive.
No, it's
and
not mutually
independent If you
exclusive.
replace it.
It's not mutually exclusive. Cards are not mutually exclusive because you can have a blackjack.
You would try to pull like 3 blackjacks. You
Yeah, and that is what
You can have
variables.
But that means,
you're
but then it
talking
wouldn't be independent if you put it back in, or then it wouldn't.
I
be
want to.
even-
You see,
It-
I
it
want to
depends
keep
on the
them separate.
context.
I want to keep them
I
separate.
understand the definitions, and I could like kind of figure it out.
If you can't
I
figure
got
it
it.
out, that's gravy to me. I'm not.
Yeah,
me,
I guess
I'm
I
not-
just have to base everything on context. But when they give
Yeah,
us
it is
no
independent.
context, that's when it trips everybody up.
That's why I don't want to go into it. Got me? If we know,
So wait.
understand it separate, you're okay.
Can I just ask this though?
Yeah.
Yeah.
When it says it's mutually exclusive, is that when the probability of A and B equals 0?
Yeah. So this would be
Oh, that makes sense. That makes
yes.
If
So if it is mutually exclusive, yes, it is.
sense. Then it doesn't.
Think of the
matter.
graph as the Venn diagram as they don't intersect.
Yeah.
If it's no, then there's going to be a little bit in between.
Yeah, that makes
Think of this as if it's no, then the probability of A and B does exist.
Okay.
Got me? So it equals a number.
Yeah.
But over here on the yes, that means the probability of A and B, and means the intersection, is actually equal to 0.
Yeah.
That's the definition of mutually exclusive. Okay? So if you remember that, if you could go through that, that might be something just to kind of go off of. Okay? So if I were to do mutually exclusive, traditionally we use it with our OR formula, where it's probability of A plus probability of B minus probability of A and B. If this is mutually exclusive, then we can actually throw this out because that would actually be equal to 0.
Yeah.
If it is not, the reason why we have to subtract the A and B is we can't count it twice. Does that make sense? Okay? And that's why we have to subtract out of it. That's using part of the formula, but again, I always go into my
And
graph first.
is that
okay?
formula you said given on the formula sheet? I believe you were saying the probability one.
Yes, it is.
Okay.
The only difference is that the OR
Is
has
the
this
U
little
shape.
U.
Yeah.
Mm-hmm. Just be careful of that. And then the and would be an overarching umbrella.
Oh, the other way.
Okay. Be an umbrella. Now, independence, I always use the tree diagram with this. Say, Coach, why is that? Well, if I said, we'll say 40% versus 60%, 40% of the, just saying,
Can we just do the cards? Or no, you can't do that one. I feel like that one makes the most sense to me.
I'm trying to think. So let's say,
You do the dice.
I like the one I used yesterday with the speeding. Remember that?
Oh yeah.
Speeding.
What do you
So
mean by that?
40% of people at seniors at GAC speed over 10 miles per hour.
Yeah, no, it was when Jarrett was asleep. Cause Coach J goes, yeah, I thought of that because Jarrett right there, and Jarrett was asleep.
That's right.
Coach, you was sneak dissing me while I was sleeping.
Yes,
Oh,
he was,
yeah.
I don't think
You
you
deserve
knew
that.
that he was asleep yet.
So this would be caught versus not caught. Got me?
How would you be caught for not speeding?
If you admit to speeding, but no one pushed you
No
over.
one
I
pushed you
guess.
over.
Yeah.
You want the highway going
That's.
90
I mean,
miles.
that's a good point. I mean, if you're not speeding,
You don't
would
get
probably
caught.
not caught. Be
You
get
don't
caught.
get caught
So
for
we'd
not
say
speeding.
0. Does that make
Yeah, but,
sense?
like,
0.
you're speeding,
Or
but,
you're not speeding. You just get caught for something else. Like
Yeah.
your
Sometimes
lights
just,
out or
sometimes
something.
you just get caught. They just pull you over.
Okay. Yeah. Okay.
All right, we'll say 10% versus 90, just so
I
that
didn't
we're,
get caught for not speeding.
Right.
just go with the
Come on,
illustration.
go on.
All right, so the caught versus not caught. If you speed, would be, let's say you get caught 40% and not caught 60% of the time. Okay? I know that's like off, but just go with me. So if we were to do this, this is a dependent event because as I look at this, depending upon whether you speed or not would have an impact on whether you were caught or not caught.
Yeah.
Makes it much easier to do this. Now what you would do is do 0.4 times 0.4 to get 0.16, 0.6 times 0.4 to get 0.24, 0.6 times 0.1 to get 0.06, and 0.6 times 0.9 to get 0.54.
Yeah.
All of these should be added up to be equal to 1, but what you are doing is saying, and what I could do is say, given the fact that you speed, what is the probability that you will get caught,
Okay.
right? That actually would be 40%. But if I say, given the fact that you are caught, what is the probability that you sped? You could actually take these two, add them together, and then you would say 40 over whatever the total was once I multiplied.
On one of the 2016 one we took in class, there was a question like that with the green light and the red light, and I tried to set it up like that and it didn't work. So they gave us the top two, but not any of the bottom two.
I'll have to take a look at it and see the
Okay.
context of it.
Can we do this one?
Go from there. What's that?
Can we do that one?
This one right up here? Yeah, we could.
Because we have to rush.
Yeah, what
There's
time
like
is it?
30 minutes left.
Do I only have 30 minutes left?
No, your hour and a half.
I have 30 minutes left of an hour and a half? Oh man, I didn't get to happen. I'll do this. I might leave
You were
the
like,
FRQs.
this is gonna be an hour and a half.
How
And
many
then,
sections are
We're just
there?
going through a lot of questions, so that's
Are there
which is
other
fine.
sections, like
So
the-
this would be
the stat medical?
0.16. This would be
oh yeah, there's 7
0.24,
sections of
And we're on
Saturday.
section 4.
0.06, 0.54. So all of these four would be combined to equal 1.
Yeah.
So if I say what is the probability that anyone at random would get caught, no matter what,
6
it would
plus
be-
0.1.
yeah, so that would be 0.22. But if I said given the fact that they are caught, what is the probability that that individual speeds? What we're going to do is then we're going to get rid of those that didn't get caught.
So do you do 0.22 divided or like? Do you,
0.22 would be the bottom
oh, okay.
because that's the
Given
given.
that they are caught.
What is the probability that they speed? So we would just be
1.16 over 0.12.
exactly. That is the probability that would be there. And if I did that, 0.16 divided by 0.22, we'd
Why is
get
it for
what?
0.22 exactly?
0.22 is just because it's given the fact that they're caught.
Oh, so you have to, okay.
Got me?
So you have to see the probability of them.
Mhm.
I got you.
And actually, you could try the one down below, which kind of is the same type of thing we just did.
0.72727272.
Yeah, so we would say 72%, this is just made up data, but 72% of the time, if you get caught, that you were actually speeding, based on this. Cool?
I think it's more like 100%, but
Probably. Yeah, but that's okay. All right, questions on that? All right, we're going to go into our next chapter. We're on chapter 4.2. Wow, we are going quick. Right now, describing the distribution. I don't want to hit this too hard because this is going into made free throws or not made free throws. We now are going to go into our bins. What that means is binary, independent, set number, and a success percentage, right? We call this a binomial. Yesterday we talked about this idea of two different ones. PDF is where it's a set amount, or what I like to call from Michael the perfect P amount. So like 8 out of 10 free throws. Cumulative would be any number, probability of a number, and anything less than. Okay? So let me give you an example. What is the probability that the basketball player makes exactly perfect 80 free throws? This would be a binomial PDF. Make sure you do the NPK. All right? Make sure you plug that in. Make sure you state the formula if it's a FRQ. N would be the set number, 100. Probability is that he's an 85% free throw shooter, and K would be 80.
So if they give you like you want this amount, then that's when you do PDF.
Now on this one, find the probability that the player makes at least 80 free throws, okay? So you got to think that he could make 0, all the way up to 79. Would you agree? Then it stops, and then it goes from 80 to 100. Got me? This is the scenario. I love visuals. They help me out a lot, okay? So what they say is that right now, we want to know at least 80. We want to know this. But cumulative only gives you the number or anything less than that number. So because of that, we've got to do binom, CDF, NPK. All right, still plug it in, where N would be the 100, P would be 0.85, and K would be 79. Got me? So if I did that here, that would be second bars. Make sure, before the AP exam, I would make sure that you just kind of look over all this stuff, just where everything is. 100, 0.85, and 79. Now that right there gives me the probability of getting 79 or anything less than. That's 0.066. So no, I'm joking. 0.066. I would then subtract this by 1. So I would just say, okay, this minus 1, I know it's going to be negative, but we would get 93.36%. Cool? All right. Visuals help. Make sure you put down the formula, make sure you plug it in, and then give me the answer. Okay? And then also describe what each of the variables are in the problem. N would be the 100, make sure you describe that. 85% free throw shooter. K is the set number, or anything less than that number, depending on whether it's PDF or CDF. All right. We're good? All right. I'm hoping that this is somewhat helpful. Let's just keep going. Okay. The number of hours of sleep, okay, so we got this. All right, so the number of hours is listed up above, right? The mean, I'm going to give this to you. You know how to find it. This would be 6.4. This would be 1.51. And the variance would be 2.27, okay? If we transform that by giving it into minutes, can I multiply 6.4 times 60?
Yes.
Yes. Okay, if I change it, the standard deviation, can I multiply by 60? Yes. For the variance, though, on this instance, you're going to have to take whatever this is 90.6, and you'll have to square the standard deviation to get to my variance. Okay?
Are these numbers given?
Yeah, this was if I did one bar stats
I
up
see
here.
them down there. I see them below.
I just don't want to even go in. Yeah, and it's down below as well. All right, number of minutes of sleep with 20 minutes of nap. So if I added 20 to each of these, would the mean be affected?
Yeah.
Yes, it would. Yep.
Yeah.
Would the standard deviation be affected?
No.
No effect. It would still be 90.6. Would the variance be affected?
No.
No, it'd still be 90.6 squared. Y'all follow me on this?
Yes, sir.
Okay. We did this yesterday, but just making sure. So with the mean, it is affected by everything. Standard deviation, so this is affected. Standard deviation is not affected by adding or subtracting, and neither is variance. Y'all tracking on that, how I did that? Okay, what if I added two things together? So if I added two means together of x for the first hour and the second hour, can I add the two means together? Yes, I can. Right? Can I subtract the two means together? Yes, you can. Okay? If I find the standard deviation and I take that and I add them up, I can't simply add standard deviation, so we square it. We square it, and then we take the square root of it. Y'all tracking? Even if we subtract, we do the same exact thing. So square root of 1.51 squared plus 1.98 squared. Same thing, whether we add or subtract. Okay? Now, as far as the variance of this is where all you need to do is just find the variance and add them together. So if I found the variance of this by squaring it, right? So let's say we did another column or row, and we did 6.2 squared and 1.98 squared. I can add variances and still be okay. All right, so what we would do is just say 6.2 squared plus 1.98 squared. That would be it. So 6.2 squared plus 1.98 squared, and that's it. Okay? All right, are y'all good on that? Okay, cool. We are going in a hurry. How much time do I have left? A lot? Good.
Okay.
When's your new time?
10:15.
All right, difference here. Example, it says find the probability that A, say A.
Hey.
A, very good. A randomly selected day. This is not a sampling, it's a sample, okay? Couple things on the top. The number of daily views at StatsMedic follows an approximately normal. Highlight that. That automatically means that we're using a normal distribution, okay? And it says that the mean is 15,000, 15K, and its standard deviation is 4. So we'd say 15K, comma 4K, which is mean, comma standard deviation. The question is find the probability that a randomly selected day has more than 20,000 views. So here's 20K. We go to the right, we highlight the right. We know that this is our p-value, right? All right, so how do I set this up? Well, I use normal, CDF, lower, got to write it out, upper, mean, standard deviation, right? And I plug it in. Make sure you know how to use z-score too, okay? Please make sure you know how to use z-score. Because sometimes they want you to go backwards, and if you don't know how to use it, you're going to be in trouble. Now, for an FRQ, you're okay, all right? But if you did the z-score, this would be my value minus mean over standard deviation. Okay, so make sure. Then you would go to table A.
And what is the value again?
Value would be 20K
Oh, okay.
minus my mean divided by my 4,000.
So the value is the value that they're asking for, which
Yeah.
is 20,000. Okay.
Correct. Now, for this next one, everything stays the same. The only difference is they want the bottom 5%. So this would be 5%. Think of this as not, and by the way, this is a p-value. Here, this is more, we're not talking about a 4-step process, so that would be more of a probability, right? The whole thing's 100%. What would be the probability? This time they gave 5% as my probability. If I said you have to use z-score, okay? You have to use z-score. By the way, you could use inverse norm, okay? Which would be my percentage to the left, that'd be 0.05, comma, mean, comma, standard deviation. Okay? That you could use inverse norm. So the percent, mean, standard deviation, you could plug it in. But z-score, we would have to actually find our z-score by going to table A and finding where 0.05 is in the middle. And you're basically finding what is the z-score, what is the z-score of that value. Okay? Are we good so far? All right, and once I find that z-score, you could work yourself backwards by doing, again, we're doing our value minus mean divided by standard deviation, write it out there, equals z-score. So once I find my z-score, I plug it in here. I've got my mean, I've got my standard deviation. You'd find your value. All right? Y'all good? All right, we're going quick here. That is a sample, just a heads up. Sampling distribution is when we have a sample of a sample, okay? Just trying to look and make sure. All right, here's the difference, statistics and parameters. A statistic would be p hat. Parameter would be p. X bar is my statistic. Mu is my parameter. S of x is my statistic. Sigma is my parameter, right? P1 minus P2, hat, that would be the hat, right? Is estimating the true difference of P1 minus P2, and so on and so forth, right? All of these estimate my population. A lot of times we don't know the population, so we use a statistic to estimate it. That's when we move into the sampling distribution, which eventually moves into my 4-step process. Boom. All right. So I just dabbed, just so you know. All right. We want to estimate the population that's here Find the average word length for Beyonce's Crazy in Love. If you remember that was one of the best activities ever.
You don't remember that?
Beyonce.
No, the way he said it.
Beyonce.
Oh, he's like Beyonce.
Beyonce's. Because he was adding an
No.
S.
Oh no, Beyonce. Is that right?
Yeah.
Isn't it? What is she called? Like the queen,
Queen who?
What?
What are you talking about?
queen, aunt, queen.
Queen Bee.
Oh, Queen Bee. I'm joking. That was bad.
I
That was
was
bad.
like, what are you talking about?
I don't know. I'm good. I'm good. All right. So, if we remember, we take a sample of a sample. Now, remember with Beyonce's Crazy in Love, we had all these dots. Right now, I know.
I was really not knowing where you were going. I was
Yeah, I was
like,
confused
oh,
by it.
okay.
All right. So, if we did like this dot plot, right?
Yeah.
And let's say that each of us took a sample size of 5, we averaged them together to create one dot of that average. Okay? Question. If I did another dot plot below, and I'm not, that did 10, what would happen to the variability?
If you, the variability would decrease.
Decrease. As we increase sample size, the variability decreases. Okay? And obviously, that makes sense because I'm averaging 10 values together.
Yeah.
Okay? So what makes a great statistic? 2 things. We have to have low bias and low variability. Very important. You got to know that. Okay? Low bias. How do I decrease bias? Yeah, how I sample. How do I decrease variability?
Increase your sample size.
Higher
That's what that was.
sample size. That's all I'm looking for. Okay? Questions on that? A sampling distribution is every possible sample of whatever the size is in the population. Is that realistic? No, it is not. So a lot of times when we're simulating, we don't do every possible sample, but we use it as an estimation there. Okay? Bingo was his name though. Okay. Here we go. This is just for you.
What?
What?
You okay?
I don't know what's
I don't
wrong.
know what's wrong. All right, so a couple of things here. This is a beautiful representation of a sampling distribution, okay? For sample proportion versus sample means. This is a very, very good idea to maybe get down. Write it down, put it down there. One thing I did forget is this is mu of p hat, by the way, equals p. But as you look at it, you've got your statistic, you've got your shape. Remembering that this is the law of large counts. Law of large counts. You've got to decipher. I'm telling y'all are going to have a struggle if you don't decipher between the two. So notice the difference between the conditions of normality for the sample mean. You have 3. You only need to pass 1. You only need to pass 1 here. Once I do, I can stop. Versus just 1 condition for sample proportions, okay? So notice the difference. These formulas over here are very, very, very important, okay? Now, question. We're moving into 4th step here. Over on this side, on the left side of the sample proportions, what did we remember about the table? What table do I use over here?
B.
B.
Table A.
Table B.
Oh, table B is
Z star, Z score, table A, okay? Now here's the kicker. If we do not know the standard deviation of the population, so this is a huge question mark, okay? Now, if I do, then we can go into it, but realistically, if I had the population, would I ever need to do, why would I estimate the population if I already knew it?
Yeah.
Does that make sense? So traditionally, on a realistic level, we have S of X over square root of N, meaning we take the sample by square root of N. That means it's not exact. Therefore, we go into what table for this one?
B.
We go to table B because we don't know what the standard deviation of the population is. So because of table B, we actually use a T star that also involves degrees of freedom, which takes our sample size and subtracts it by 1.
Yeah, and if you don't do normal CDF, you do TCDF once you find the T star. Right?
We do TCDF as we go towards that. Yep.
Yeah.
Okay. Are you Gucci?
Yeah.
Mhm.
By the way, the value minus mean divided by standard deviation is the same
What?
for t-score.
Okay.
T-score. If you did it backwards or if you worked on that. But remember that when we're doing that there, okay? All right, are we Gucci? I hope this is somewhat helpful. Okay. All right, as we go.
He's on you. He's on you.
Oh man,
Wow.
this is a great day, guys. All right, so as we go
He's on you.
to oh man, I almost made a joke on Preston. I'm gonna hold off on that. I'm gonna hold off on Preston's joke. I know Preston. Now I'm gonna hold off. All right. So as we go towards it, I think that is it. Okay. Sampling distribution for two populations, we kind of build off of that, right? I would say, I was trying to think of what I would write down here. Do y'all want that information for two? Would that be helpful?
We don't have enough time.
How much time do I have?
Like 13 minutes.
Are you estimating?
Well, we started at like 9:45.
Okay. Hey, this is just, I'm going to write down the shorthand here. So this is x bar 1 minus x bar 2. We use this to estimate the population, right? Traditionally, when we're going into
Don't click OK.
two sample.
Don't click OK. Don't click OK. Yeah, coach.
Yeah.
Very good. Get out of here. All right. All right. So as we go towards the shape, what we've got here is we've got two different types. Okay. We've got n. Usually it's n times p is greater than or equal to 10. It's n1 p1 is greater than or equal to 10, and n1 or n2 p2 is greater than or equal to 10. Over here, though, you've got to do n1 times 1 minus p1 is greater than or equal to 10, and n2 times 1 minus p2 is greater than or equal to 10, okay? Law of large counts. Got to do it for both, okay? Got to do it for both. On the second one, for the two means, you've got to make sure that it passes both, right? So population is approximately normal or normal. The second one is CLT, n is greater than or equal to 30. And then the third, we go into the graph. If you're confused, go to the other one, but we've got to do this for both, okay? The center would be the mu of p hat 1 minus p hat 2 is equal to p1 minus p2. Remember, it's the same thing, just the subtracted version. Over here is mu of x bar 1 minus x bar 2 is equal to mu1 minus mu2, right? It's the same thing what we did beforehand. Just notice that there's a difference, right? There's two of them. Cool. All right, so this is where the variability comes into play. Recognize it is all I need you to know, okay? You recognize this, that's all I need. Once I get to these on either the confidence interval or the test, this would be in the do phase. You could always use your calculator as long as you remember how to, or what's expected on that 4-step process, okay? So I'm going to put this down, but I'm going to do it really, really quick,
We
okay?
have to show what we put in the calculator. We have to put t-score and
The graph.
the p-value, and the graph. Right?
Yep, graph or p-value. If it's a confidence interval, put down the confidence interval.
Yeah, because what they were saying was like with the z-test, like if you're gonna say p combined, like you have to make sure that like your math is like really good.
Yep. Otherwise, it's hard to get credit if you put nothing down. But on the 2-step, you can, right? On the 2-step, you can. That would be the standard deviation of the difference. Okay.
It's over.
10.
I gotta go to 4th period.
Dr. Dan's class.
Y'all do? Y'all have to go there? Oh.
I'm going because I got AP Macro 4th period, so I didn't go study for that. I got that exam tomorrow. That's a rip.
That's awful.
We got fun.
I have 3 AP exams. I took 3 AP classes this year, and they're all like this last 3 days. Like they're not spread out at all.
Traditionally, we don't know what the standard deviation of the population is. We would put that in there if we didn't. But that could be the sigma as well if you did know it. Okay.
How late are you staying, Coach?
Today I'm going till 11 for this one.
Oh, 11?
Yeah, what time is it?
10
I
over
thought you
10.
said 11:30, but
If I go 11:30, that's fine. I can go 11:30.
Yeah, it might be-
Z-score?
I'll be back at like 11, so I'll see if you're still here or not.
Perfect. Yeah, come on. Z-score is value minus mean. Okay, so this is where it comes becomes weird. This would be like p hat 1 minus p hat 2. All right, that would be the value. The mean would be p1 minus p2. And the standard deviation would be everything that I stated up here would go down here.
okay.
Does that make sense? Over here on the second one, the z-score is value, which is x bar 1 minus x bar 2 minus my mean, which is mu1 minus mu2, and then divided by my standard deviation, which was up here.
But the P1 minus P2 and mu1 minus mu2 is usually going to be 0, right?
What's that?
The P1 minus P2 and the mu1 minus mu2 is usually going to be 0, right?
Yeah, usually the difference is going to be 0 when we're talking about a 4-step process. Yes. Okay? All right, so that is it on Chapter 5. That was actually not awful in terms of timing. We just have all of Chapter 6, which is our
Do we really have to go over
4-step
the
stuff.
4-step process? Can we just do match pairs? Or chi-squared? There's no offense, if you don't know that by now, like...
How about this? Yeah,
I
how
feel like we've done this like 500 times that if you don't know it by now,
it's
like,
sickening.
or just know the gist of it.
here's what I would say to this. Look over your notes on all of your StatMedic stuff, okay? So as you look at Chapter 6, please look over your notes on that, okay? Please do. So there's a lot of things that can be easily forgotten. I'm just saying don't forget those, okay? Write down your formulas, right? Make sure you show everything within the one step. So the ones you'll need to show work for is, and again, how I would look at this is 95% confidence interval to estimate the true mean of a small order French fries at this restaurant. One sample, right? T interval. One sample T interval, right? If I look at this one, it says construct and interpret a 90% confidence interval for the true proportion of people in the city who would support changing the law. One sample Z interval, right? You see the difference? I'm just looking at the last sentence. Construct and interpret a 95% confidence interval for the true difference. Well, what would that be? In proportions. So that's a 2 proportion Z interval, okay? So the do phase, you do not have to show work on. You would put in as a 2 proportion Z interval and put in your stuff that you have down, okay? Make sure you look out your calculator on how that goes in there, okay? Perfect. All right, look at just at the top here. This just pulls from what we have. 100 volunteers are randomly assigned. So question, at the very end, I'll conclude it the same way. We're 95% confident that the true, whatever we're talking about, true difference in proportions of people who had the medication versus those who didn't fell between this to this, right? Question, if we, okay, at the end, actually have this. This is good. This is really good. I am going to just stay home just for a second. When we did this, it was between negative 0.073 to 0.273, right? Question. Do we have convincing evidence to say that the medication does in fact reduce the cholesterol level? And why?
It'd be, yes, it'd be on both sides, negative and positive. So it's,
We would say since 0 is included within the difference.
that's what it is. 0.
0 is included in the difference. We do not have convincing evidence to say that the medication, in fact, reduced the amount of cholesterol. Very important. This is really, really good. Okay? All the other stuff, again, you know how to do state, plain, do, conclude. If you don't, then good luck. I would say in this instance, though, because 0 is included, we do not have convincing evidence. Now, what if both were positive? Say they were both positive. We would say that 0 is not included. Since 0 is not included, can I say, in fact, that the medication caused a decrease in cholesterol?
What?
Since 0 is not contained in the confidence interval, do we have convincing evidence to say the medication did, in fact, reduce the cholesterol? Yes, we can say that, but why? Can I have a cause and effect, though?
No.
Read it. Read it now.
Oh wait, no, it's an experiment.
Read it. Some key things randomly assigned, right? Because it's randomly assigned, I can in fact say that there is a cause and effect relationship if 0 is not included
So
in my
random
confidence.
assignment. Okay.
Allows me to show that cause and effect. You see how they all kind of wrap up together?
So, if zero's included in the 95, then you can't conclude?
If 0 is included, that means we do not have convincing evidence that
Yeah.
that it's favored on one side or the other. Therefore, we do not have convincing
Why
evidence.
is zero in there? If that's a is that a
Oh, no, this is a negative.
Oh.
I was just messing with it. Yeah. Cool. All right, we're good?
Yeah.
All righty. This is just the same thing. 99% confidence interval for the true difference in mean. 2 sample
But
T.
if it wasn't randomly assigned,
interval.
it was just random sample, and you asked the same question, you can't.
Cannot conclude cause and effect.
Yeah, you
So
can't. You can conclude that it is, but you can't say it caused it.
You could say it's convincing, but there's no cause and effect relationship. Great job. Alrighty, at least one of these are on the AP exam, so just a reminder of this. It says, does the data provide convincing evidence that the shop is not selling true Chicago-style popcorn? Well, convincing evidence tells me that it's going to be a test. The 40% caramel tells me it's probably proportion. 500 is my sample size, random sample of that. And we find that 183 are
So it's
caramel.
Z test
So it's a 1
proportion.
No, wait.
proportion, you're right.
Z test.
Z test. Just as a start, we know that the null would be what? P is equal to 0.4. Now, what did you say? 0.25?
I said 25.
Where'd you
I'm
get
talking
25 from?
Yeah, I'm talking about.
Oh, you're good. Okay, so we know that P is equal to 0.4. The alternative says that,
P is less. But they're not selling their cheese. Oh, it's not equal.
It's
it's
great.
not equal. I would say it's not equal to, right?
Yeah.
Because it
The
says,
P hat is 0.36.
oh, it says, is it less than? A new popcorn lover takes a random sample and finds that the shop is not selling true.
It's just that it's not selling true.
If you said greater or less than, I could see less than. But
I can see less than based off what the P hat value is.
yes, but I would say that up here, I would say not equal to.
Yeah.
That's what I would say, but in my notes I have that it's less than. Because if it's less than 0.4, then we're just saying that it's not Chicago style. That means it's not 40%. But if you did the other, that'd be fine too.
But not equal to would be fine. That's it.
Fine. That's what I would go with in this case.
Yes, sir.
P hat would be the 183 over 500 when we actually test this, right? 0.37 would be my P hat value. Now, as I do this, make sure you define what is P, right?
It's the true proportion of true
Of
Chicago
caramel-
style popcorn.
Yeah, caramel popcorn in the whole thing, right? To get you.
True Chicago style caramel.
Yeah, I just put true proportion of popcorn in the Chicago style that is caramel.
Oh, okay.
Okay.
It's good. In the plain phase, make sure you hit your 3. Random, normal, and 10%.
And
And make sure that make sure you put the name of one when we have it right there. One proportion z-test. It's fine. On the do phase, make sure that when we do this, we have our mean. Our mean would be 0.4. You say, Coach, why is that? Well, mu of p hat would actually be equal to p, which we're assuming that 0.4 is actually true. Okay, we assume it to be true. The sigma of p hat is equal to square root of p hat times 1 minus p hat all over, or p times 1 minus p all over n, not p hat. I'm sorry. So p would be 0.4 in this instance. 0.4 times 0.6 divided by n, which is 500. I'm taking this a little bit further just so that we've gone through one, y'all. This would be, I didn't get the full thing on that. It would be, well, something. We would plug that in, right? We'd use 0.4 here, and 0.37 is to the left of it. But because if we use not equal to, whatever this is, we've got to also mirror it over here. So we have to multiply that by 2, right? Make sure that if you did use normal CDF for one side, make sure you also use the formula, right? So normal CDF, I'm not going to write it all out, but lower, upper, mean, standard deviation, make sure we write that in.
Do we still have to do that?
We
Like
do.
normal CDF?
Mm-hmm. If you use it, now if you use z-score,
Oh,
you
yeah,
just
yeah,
write
yeah.
that formula down, and then go from there, okay? All right, are we good?
Yes.
Conclude, are we good on concluding?
Yes.
Okay, cool. If we're not, then we'll do it on Wednesday too. Come in on Wednesday and hit it. All right, context, all that. Okay, cool. Next one. I always read the last sentence, just how I roll. Does the data provide convincing evidence? I know that that's a test. That AP Stat students spend more time on homework per night than last year. Well, I'm comparing more time from last year to this year, so that's going to be a 2. So 2 sample test, and whether it's T or Z depends upon the mean or proportion. In this case, it's going to be T because we're talking about mean, right? So last year, they spent an average of 25 minutes on average, and this time we used a random sample of 30.
Well, are you sure it's a 2 sample?
Yeah, it's a 2 sample.
I don't think it is. I think you're just proving if it's greater than 25. Because you don't have all you have is a mean for the last year. Because you don't know how many the sample size of last year.
Yeah, it doesn't.
Oh yeah, good point. So it says last year an AP Stats class spent an average of 25 minutes on their homework. Their teacher randomly sampled 30 of her students this year to see if this average had gone up. A sample had a mean of this and a standard deviation of this. Yeah, I would say because we don't know that information from the first one, this could be 2 if I knew that. But because we don't, we'll just simply do one sample, where the null would be that it would be the same. Mu is equal to 25 minutes. And the alternative would be that mu is greater than 25. Where mu is the true mean true mean time spent on homework for the second year. Okay? All right, we're good there?
Yeah.
All right, now we're going to go into the next one. I want to show you the difference here. Does the data provide convincing evidence that there's difference? Oh, that's the key. If they say difference, we know that that's going to be true, or a 2 for this.
2 proportion Z.
Yep, 2 proportion Z test, okay? Do not have to. When we do a 2-sided, or when 2 proportion Z test, traditionally the null is going to be equal to 0. The difference will be. So null would be P1 minus P2 is equal to 0. And the alternative is that P1 minus P2 is, there's a difference in the proportion. So that'd be not equal to 0.
So with the state part, so I usually identify with the parameter, stating the parameter. I just say there's the true difference in proportion. But when do I have to put for the p hat value, because there's gonna be a p combined? Do I have to put P1 minus P2?
If you define
P hat 1 minus P hat 2.
yes, I need you to put that. So I need to find this based upon,
Just have to.
yeah, so the first one would be 450 of 500 minus the 342 over 400, and then I would find what that sample difference would be. I'd also need to define what P1 minus P2 would be. Make sure we define that, right? True difference in proportion of job A or college A versus college B for recent graduates who got a job, okay? So obviously in this case, we would probably say the higher of the two would be more representative of Michigan, the lower one would be more Ohio State. Good? Good. All right.
Yeah.
Nicely
Try
done.
to slide that in.
Yeah, that's good. Make sure in the plan we also do random for both. And then in the normal for both, make sure we know the three conditions. Or I'm sorry, this would be the law of large counts. So N1, P1 greater than or equal to 10, N2 times, or N1, sorry, times 1 minus P1 greater than or equal to 10. You have to do the same thing for 2 as well. Okay? Greater than or equal to 10. Make sure that that all is true. Number 3, 10%, and you would do it for both. Okay? All right, we are good there. Does the data provide convincing evidence that the mean score was higher than the mean of B? Yeah, and because they gave us both A and B, we would just go ahead and just say, okay, the null is mu1 minus mu2 is equal to 0. The alternative, that A was higher, so this would be greater than 0. And then the same thing before, right?
Yeah.
Not really a huge need. Make sure we plug it in our calculator, but this would be a 2-sample t-test. Okay? I know I'm going through this quickly. Good.
Mean of differences.
Is that what this is
That's
here?
match pairs.
Yeah, this one on 7.3 would be match pairs. The difference of means here,
Mean of difference.
where we have 2 samples, but we actually...
Like they were talking about like doing how you identify it as a match pair.
Yeah, so this would be more mu1 minus mu2.
Yeah.
Because what are we doing? We're taking the difference of just the means. So 87 minus 80. So x bar 1 minus x bar 2 would be 87 minus 80 to get a difference of 7, right? That would be the difference of means. The mean of the differences would mean that I'm literally taking just this column, okay, or row, sorry, that row, and finding that the difference would be 7, right? That means that the null would be the x bar diff is equal to whatever we're trying to prove. Let's say it's, I'm sorry, this is mu diff. If we're doing a,
Match pair.
match pairs
The mu-
test. So mu diff, let's say we're saying that we think that the difference was 5, but we say that the alternative of mu diff is greater than 5, okay? We would say the mu diff is the true difference between version A and version B of the final exam. And then we would write down our alpha level of 0.05. On the plan phase, that would be the exact same, right? On the do phase, though, just so you know, like the picture, the middle would be 5 because we assume it to be true. The 7 would be over here on this right side. And the standard deviation would be 7.52. And then I would just simply find what that highlighted area or p-value would be as it relates to the sample to the right, okay?
So-
There's a difference. This would be match pairs. Go ahead, Ryan.
When that's not well, for match pairs. You don't write information, do you?
Right information.
Like when you talk about the hypothesis, the null.
Yeah, I would act like defining what mu diff is. I would just say mu diff is the true difference between version A and version B test of the final exam.
I don't have to
Or-
say anything about them both taking both finals.
That might be a good idea. Yeah. I would, because it's the same person, right?
Yeah.
Same person.
What do you name the test? Match pairs t-test?
I've heard
T-test.
paired t-test.
T-test.
Yeah, I've seen one sample. No, it's probably match pairs t-test or paired t-test. That's fine. Cool. Chi-squared.
Oh,
Y'all need this one?
yeah, I hate chi-squared.
All right, we're almost done. We are almost done. Okay. If you need this, here's the thing. The AP question, do y'all already have this on yours?
Yeah.
Yes, sir.
Okay, I'm not going to go into that, okay? What I will say is that this is where we compare to a standard. Think of the gummy bears, okay? The gummy bears, the package says it's this. We tried to compare it and say that it actually is not, okay? So we would say that the null is that the claim is true. The alternative, obviously with a lot of context, claim is not true. The expected would be the n times p, so the sample size times the proportion, and we would do that for each. So if I say there's 40% red in the package, right, and that's the claim, the expected amount would be 40, and say we have 100 gummy bears in our sample size, we would do 100 times 0.4, and we would expect that there would be 40 red gummy bears. That's expected, okay? The degrees of freedom on this would be just simply n minus 1, or categories minus 1, not sample size. That's a little different. I want to make sure that that's clear. Categories minus 1, not sample size minus 1, okay? So if I had 4 different categories, that'd be a degrees of freedom of 3. To be able to do this, this would be chi-squared is equal to the sum of observed minus expected squared divided by expected. Make sure you show a couple of those, right? Remember the ... part, observed, expected, all that, okay? I would definitely find the expected, put that in maybe the plan or right at the beginning of the do phase. The p-value, in the context, well, I think you know p-value, right?
So we don't have to draw a picture or do like.
I would just draw a picture. Remember, it's skewed to the
yeah.
right on that, but I'm going to say that it's the same all the way across the board.
And we don't have to put
that.
like means. I don't remember.
The expected, no, there's no mean or standard deviation. No mean or standard deviation. The way that I plug this in for this one is I'm going to use the one. I'm going to go to my list. Y'all remember that? So when I go to stat and I go to edit, I'm going to make sure my list is comprised of the observed. Y'all follow me on that?
The list is observed.
Like L2 is
Or
here.
L1.
Let's see that. Yeah, L1's there,
Yeah,
right?
how'd you just get the residual?
Yeah, I'd gotten it earlier. When you go into your stat, calc, linear regression, I remember we did it in your calculator where when you do this, and you do L1 is your explanatory, L2 is your response, and you press calculate, it gives you what your R is.
Oh, I forgot about that.
Okay? So when we go into stat test, the goodness of fit test is what we're looking for. The observed would be L1, your expected would be L2. Make sure that you find the expected by doing n times p. And I think it actually calculates it for you.
It does? No.
Oh, because it doesn't know it. No, it wouldn't know it.
We didn't know that.
It's the other one. It's the other one that does that. Cool. So it gives you your chi-squared test statistic, your p-value, which is what is shaded, and then your degrees of freedom is obviously your categories subtracted from the length. Okay? Cool. Number of populations, number of variables. Anytime this is one population and one variable. Gummy bears, population. Variable is my color. Okay? All right, y'all good so far? We're almost done. Test of homogeneity. We compare samples. So 2 different types of gummy bears. Compare samples. This is going to have a matrix. This is where we plug it in for matrix A into the do part. You only need to plug in your observed. It'll calculate the expected. The only thing to remember, though, is when I plug it in, I go to stat, I go to test, I go to chi-square test, and I put in the observed. Don't worry about the expected. And then once I calculate and draw, remember we did this yesterday, or when we plug it in, It'll give us something that goes downward. Cool. And it'll give us the p-value and the chi-squared that's there. Okay. Again, homogeneity comparing two things together. So we have two variables and one population, or I'm sorry, two populations, one variable. Two different gummy bears, and we're comparing color. Okay. The degrees of freedom on this would be column minus 1 and row minus 1 times row minus 1. To get the expected, we do the row total times my column total. Hold up. I messed that. I thought I said that wrong yesterday too.
What?
I thought it was my row total times my column total divided by my grand total. What do y'all have on your notes there?
For the degrees of freedom?
I just have rows minus 1.
Yeah, that's what they told us.
I
For
thought
the
it was
expected,
total
they
too,
do
but
row
Oh,
times.
right above, right
The
above. That's
expected
it.
is row times
Yeah.
column.
expected is
Expected, yeah. So row total. I had it down wrong in my notes. Column total divided by my total total.
total.
That's the same for those.
Yep. So this is the ditto over here, ditto over here. Okay. Chi-squared formula is the same across the board. So this is the same across the board. Remember that this is how I get my test statistic. So that chi-squared, which your calculator will do for you, that is your test statistic on that. Okay. Your hypothesis. What would be your hypothesis?
There is
Distributions are the same, and the alternative is distributions are different. Right? Does that make sense? So, like for the gummy bears, they have the same color scheme. Alternative that it's not. Test of independence is that it's an association, right? Okay. Yep. So null is we compare like the effect of one on the other, right? Compare effect of one variable on another, of one on another. This would be like saying that there is one population with two variables that are measured.
okay.
Got me? We have a statistics class. Two variables are the amount of sleep compared to your score on the
So
AP exam.
how would I be able to? When they say chi-square test, or like for this, how would I know that this is homogeneity based off or like a two sample?
What was that website that we used?
Yeah,
That's
so
what
if
it says?
you come
Because,
here.
like technically, like if you.
Oh, yeah. Oh, yeah. Let me go here.
Oh.
Oh,
Yeah.
no.
We're almost done.
No, you gotta go.
I know.
I'm sorry.
I don't even know what's happening right now.
What?
GAC Wi-Fi.
Gotta love it.
I'm still working.
Oh, we have to turn our computers in. I'm gonna
When?
be like, what
When?
No, it's not. I thought it was like 22nd.
How did we turn our? I thought it said by the
I
last
don't
exam
remember.
that you had.
You serious?
I'll wait until they literally come to my house.
Yeah, I'll wait until they're knocking on the door.
Oh, man. Wow.
GAC opened
Threats
up.
on our podcast. This is good.
Uh,
All right.
he's been making fun of. Remember
He's
that?
been making fun of Charles's laugh this entire time.
He's been making fun of.
He's making fun of Charles's laugh on the video.
It's so funny.
I'm a warlord. Is that not funny? Is that funny?
My
I thought
country
you
is
can
dead.
take my
Yeah,
seat.
who said you can take Ryan's seat?
All right, let's look at chapter 11. I think it's down yonder.
What, Ryan? Ew. You still have
It takes a good
bathe.
amount of it takes a good amount of scrubbing to get this
Shower.
off. I was just like,
Go shower.
no, I have to literally scrub.
You have to scrub your cheek.
All right,
Yeah,
I
it's
think.
so little.
I
Lindsay
see it.
decided to put it on my
funny.
bed.
Huh.
I did it for Christian.
Okay.
Not really, I did it for myself.
Okay.
All right,
you know
so
what I'm talking about, the
I
coach, right?
think, yeah, no, I
It was
know.
like some,
What?
I forgot.
What
The
is it?
website we were using to figure it out, like whether it was
Who's this from?
homo
Oh.
association and stuff like that.
I don't know if I should go home and eat lunch at my house or go to
What'd you say?
I just really don't remember.
Site?
AP exam question index. No, that's not it. I'm trying to
Check
find
on
it
that
for
unit.
y'all.
You wanted to check out, what was that unit?
I thought it was 11, but I didn't see it. Let me try it one more time. That was on when we were doing chi-squared, right?
Yes, it was on our like our little review.
Honestly, everything from like what we've just been like going over for a long time has like completely jumped out of my brain.
Yeah.
Like-
I'm trying.
Like the tests, like we've just been going over that. So I can do tests for different so easily, but like I don't know. Everything else I'm just like, oh,
I would just make sure you review those. We actually,
thanks.
Ryan, did that? No, I say, no, that's, it's like a yeah, duh.
Sure you
Did that
will.
help today, though?
Mhm.
I think it,
Did you
I think
stop
we went
it?
there.
Yeah, sure.
No, we're still rolling.
Hi guys.
Go
Oh,
Jason
test
and
help.
Jared in
It's
his
right here.
basement.
That's real? Wow.
Woo! Whoop, whoop. All right,
Gosh, Jared,
so
they give